It's a great pleasure to introduce Dybjer from Mahlo University of Technology, who will talk on inductive definitions, predicativity, and the Mahlo Universe.
Thank you. Yeah, thank you, Anston, for inviting me to this very nice workshop. I'm very happy to be here. And of course, I am very interested in this subject of inductive definitions. I did a lot of work on this some decades ago. Part of it was in collaboration with Anton Zetsov from Swansea. And we have recently resumed our collaboration. So I was in a little bit of two minds about what I should focus on. One idea was to speak about my old work, so as to speak, 20 years later and recent developments and so on. And I will say some of that, but I will actually more focus on the recent work with Anton, because I think, well, it's recent work, and because I think it really fits very well in with the theme of this workshop, about, Laura will speak about predicativity, for example, in the next talk and so on. So it's more, sort of foundational research, I would say. So let me start with this slide. So now in my recent collaboration with Anton, I know we wanted to analyze predicativity. And I noticed that Anton used predicative and inductively defined as synonyms. And I was a little bit shocked by this, because it wasn't quite the way I thought about it. It could be, but not quite. So it intrigued me, but of course it means that the predicativity lines up with, let's see, what shall I do? Yeah, it lines up with the theme of this workshop. So just a little bit of a terminological slide that, yeah, so actually the work I'm going to describe will be, is submitted for publication in a volume of Weil, edited by Laura. So of course this is to commemorate Weil's work on predicativity more than 100 years ago, and his introduction of the notion of predicativity given the natural numbers. And predicativity given the natural numbers comes, technically in several levels. There is what has been very accepted as a notion of predicativity in proof theory, namely predicativity up to logical strength gamma naught, predicativity in the sense of Pfefferman and Schutte. And it so happens that Martin Löw type theory, in the early versions where you had a infinite sequence of universes, it turned out to have exactly the strength. So the paper written in 1973, it was called Predicative Part. I think even before it was known that the strength was exactly gamma zero. So several decades later, one introduced the notion of super universe. And from the point of view of proof theory, super universe, although it increases the strength above gamma zero, it's still somehow very predicative in a very similar sense. And there is the notion of meta-predicativity, which I believe was introduced by Gerhard Jäger and his school in Bern. But from the Martin Löwian point of view, predicativity doesn't stop there. In his 1979 paper, Constructive Mathematics and Computer Programming, he introduced W types, which are definitely considered to be impredicative in the sense of proof theory. But the Martin Löwian perspective is that they are still predicative, and to distinguish terminologically this, some people like Anton use the words extended predicativity. So some kind of thesis is that extended predicativity is the same as generalized inductive and inductively recursively defined. So I will talk about inductive recursive definitions later, somehow generalization of inductive definitions, which you can have in Martin Löw type theory. and that this turns out to also be identical to constructive in the sense of Martin-Löf type theory, in the meaning explanations already mentioned by Anston in his talk. So the relationship between Martin-Löf type theory and inductive definitions was strong already from the very beginning, although in the early days I don't think it was so emphasized. But there is a quote in Martin-Löf's 1972 paper, which was actually not published until 25 years later, but where this connection becomes explicit. He says that, let's see, can I... there, yes. He says that one could potentially think of have a general formulation of ordinary inductive definitions, and not only, you know, he only treats the special cases of sigma types, disjoint unions, finite types, and natural numbers. But he already indicates that one could imagine a general formulation of inductive definitions, and he refers to his own paper on inductive definitions in predicate logic. And actually, but of course, it was sufficiently difficult to get a good formulation of type theory, so it was probably a wise choice not to worry about the general formulation of inductive definitions already at that stage. But that paper, Martin-Löf 1971, was very important for me in finding the definition of you know, what it means to be an inductive family in general, what Anston mentioned in his talk. So another pointer to the correspondence between inductive definitions and Martin-Löf type theory can be found in the concluding section of Peter Axel's article in the Handbook of Mathematical Logic about an introduction to inductive definition, where he says that it would be interesting to make a framework that makes induction the principal notion. He doesn't explicitly mention Martin-Löf type theory, but he probably has it in mind because he had already written a paper on models of Martin-Löf type theory. So I take that to indicate, you know, that type theory or something like that could already at that time be understood as a general theory of inductive definitions. So as regards generalized as opposed to ordinary inductive definitions, well, they were already mentioned very appropriately in Anston's talk. They are embodied by the so-called W type, the type of well-founded trees with arbitrary varying branching. And they have the formation rule, you know, the rule that says when is a W type well formed. So yes, I should already now say that I will use, following Per Martin-Löf, the word set for the usual types in Martin-Löf type theory. I will later come to the distinction between types and sets, but let me use the word set at the moment for what in the very early versions of type theory were called types. And I should also say, since we have people in the room working on homotopy type theory, that this is not set in the sense of H set. This is a later use of the term set. Yeah, so anyway, so this is the formation rule for W type, and the introduction rule is a generalization of what Anston explained for the Brouwer ordinals. So you see here that the type A is, you think of this as a type that indices the branchings of the well-founded tree. So in the case of the Brouwer ordinals, this would be a 3-element types. And then for, you know, B of A, this is the branching for that index. So there would be one with 0 branching, one with 1 branching, and one with n branching. And then, so then you can see how Brouwer ordinal becomes a special case of this. So W types seem really important for type theory because they seem to be canonical for generalized inductive definitions in type theory. I don't know of anything in generalized inductive definitions in type theory that goes beyond W types. And there are some results suggesting this. So if there is someone in the room who has some suggestion for this, that would be interesting. In order to get further strength, you need to go into universes and inductive recursive definitions. But this is just a kind of conjecture that I think it will be quite interesting to think about. So, yeah, so I worked on this general schema for inductive types, much in collaboration with Per Martin Löv, who very kindly spoke to me on the phone, where, in trying to find a good formulation of this. Thierry and Christine Poulin did very similar work at the same time in the connection of going from the original calculus of constructions to the calculus of inductive constructions. So it's very easy to understand the general schema for generalized inductive definitions in type theory if you know the W types, because it is just a mild generalization. It's more general in the sense that you can, in the W type, you have only one constructor. Here you can have several constructors. In the W type, you have only one, what I typically call the non-recursive premises, those that don't mention the W, the thing we introduce. Here we can have finite number of them. You could also call these side conditions. And then you have finitely many inductive hypotheses, inductive arguments to the constructor. So you can sort of easily understand that this we can encode in terms of W types and that it doesn't really add any strength. But from a practical point of view, it's useful to have this kind of generalization. So when I started working on inductive definitions, I was really thinking that, well, you know, type theory, it has the following structure. We start with the pure dependent types with dependent function types. And then we have inductive types. And then on top of that, we put some kind of structure of universes. But I refereed a paper by Max Mendler, a member of the New Pearl group for Lix 1991, where he had categorical semantics of universes, putting different universe constructions that existed at the time under one hat. And I was thinking, so maybe this is related, maybe there is some kind of general schema behind this. And what was interesting was that I kind of checked, how can I modify my schema for inductive types to cover, these universes, inductive recursive types. And I discovered to my amazement that it was really, really easy. You just take exactly the same structure, but what you say is that we can simultaneously, if we think of this to be inductively defined, then it's, we are used to being able to define a function by induction on that type, as mentioned in Ansten's talk. But we are not used to letting that function participate in the definition of the inductively generated U. So the original type thing in type theory, which has the structure, is the so-called universal Hataski, which, it was not there in Per's early versions, but it came in the early 80s. It's discussed in the Bibliopolis book, for example. So if we look at two of the introduction rules, say for, then we have to distinguish between a code for a W type here and the W type itself. And the T function, it's the decoding function, which maps the code to, the type or set form that it denotes, and then you have to decode the argument. But if you look at this, you see that what is new about this with respect to the W type and the general inductive types is that the T participates here, and even negatively. And the idea is somehow that once we know that A is a member of the okay, yes. Someone wanted to yeah. I can move it. I mean, the idea here is that as soon as we know that A is a member of the universe, then we can immediately decode it and use it as the domain of the second argument for the codings of the W type. So informally, this suggests that this can be understood predicatively. And, in the previous picture, I had a structure where I put all the side conditions before all the recursive premises. And we can see that this is no longer, this generality is no longer sufficiently general, because when we have codes for identity types, it's the identity on the type coded by A of the elements B and B prime, which are, you have to decode the A in order to form this. Then these are side conditions that depend on a recursive premise here. But so with this generalization, that was all that needed to be said. So although when you read the paper about it, it seems complicated, it is intuitively not so complicated.
What was the bullet, the ring?
Composition is just a way to write lambda xt of B of x. Okay. Yes. So this talk will actually be a lot about inductive recursive definitions. So prior to these ideas about what an inductive recursive definition was in general, a necessary prelude of that was the extension of the notion of universe from the Tower of Universes a la Tarski here that Martin Löw introduced, internalized by Erik Palmgren, having universe operators that took one universe to the next, and the super universe being closed under this next universe operators, and further generalized by several people, and in particular by Anton Setzer, who introduced the Mahlo universe, which I will discuss later. And then that turns this type of set into what we call an external Mahlo universe. But I will explain what I mean by these on later slides. So Anton and we made a finite axiomatization of this earlier schematic formulation of inductive recursive definitions and defined something called IR, the theory of inductive recursive definition for Martin Löw type theory. And it includes all of these examples as special cases. But if you go one step further and you try to not have this type of sets as a Mahlo universe, but you try to define M in set, this was also referred to in Anston's talk, where you think of set as the somehow type of all kind of inductively generated sets. You want to think of M as a inductively generated thing. Then, in some sense, happily, IR does not cover that, because this is in some sense problematic. And then Anton continued with induction recursion beyond the theory IR. So one can think of, IR formulates a special form of induction recursion, which is quite powerful, but there is, of course, not an end to it, but you can go even further and sort of further into the higher infinite of type theory. And what is kind of important for this talk is that there is some kind of both intuitive and formal connection between Mahlo universes and the theory IR of inductive recursive definitions, which is sort of a bit like the definition between W types and generalized inductive definitions. So it is important for this talk to use Martin Löw type theory as it was formulated in 1986, and not as it was formulated earlier on. In 1986, Martin Löw introduced these two levels, what he called the theory of types, which is just, dependent type theory with dependent function types, written without an arrow by Per and by Anston in his talk, but nowadays I usually write this for dependent function types, and the type set. And you also have the principle that each set is also, there is also a type of its elements. And he did that partly because of somehow economy. He was very inspired by the calculus of constructions, where you had compact formulations of the inductive types in terms of impredicative quantification. And he wanted to do something equally compact, but in a predicative way. So that all the set formers, the types of them, could just be given as, they are constants. Oh, how did you stop that? Maybe it's going away. Yeah, anyway, so let me just see. Yeah, no, so the only point I wanted to make was that it's important for this talk because the theory IR and similar theory of, inductive recursive families, indexed inductive recursive definition, they're all based on this structure of type theory. And we call the theory of this talk TTM, which is somehow ordinary, all of those set formers and a Mahlo universe. And a remark is that the proof assistant Agda, developed in Gothenburg, is loosely based on Martin Löw's logical framework, but it's not exactly the same. It differs in some respects. But it's sufficiently close so that you can implement the most of these ideas in Agda. So this slide is only to show how the universe Alatarski comes out when formulated in LFs. You see, the difference is that T now has a type. It stands by itself. It's not a unary syntax constructor that takes one argument. It stands by itself. Similarly with the codes, it's constant with this type rather than a binary term constructor. Similarly with ID hat, and the equations look the same. Yeah, so in order to understand what Mahlo universes are about, it's worthwhile looking a little bit closer about what super universes are. This is the first step beyond the external hierarchy of universes. So what Erik Palm, what Erik Palmgren did was to define a next universe operator. So if FAM set denotes pairs of sets and families over that set, it takes something in the sequence and maps it to the next as an internal operation. And then he defined a super universe, which is closed under this next universe operation too. So now you have a universe which is bigger than any of these in the sequence. And using exactly the same idea, you can have a next super universe operator and the next, and you can have a super universe, and you can have a next super universe, etc. So if we understand how this works, the next step is to go to say that there is nothing special about next universe operator or next super universe operator. It's completely generic in some operator on families of sets. So we can think of a universe Alatarski, U of, and then we split up because of some formal reasons, this family operator in one that returns an index set, and the other which returns the family. And then we have decodings of that. So we can formulate rules for universes closed under arbitrary such operators. And then the type of set assumes the character of a Mahlo universe. And we call it this version external Mahlo universe because for the reason that I already mentioned. And we think of all these U of Fs for an arbitrary F as sub-universes of set. So formally in LF, it looks like this. This is the formation rule for subuniverses. It simply says that if we take a family operator split up into two components, returning the set and returning the index set and the family over that index set, and similar decoding, then this is a good set. And now if we want to build a universe closed under that, we have a universe a la Tarski. So we have to make a distinction between the family operators F0, F1, and the things which build codes for those inside, those things which I wrote with hat before. But here I prefer to use the letter C for constructor, C0, C1, emphasizing that this is a constructor while these don't need to be constructors. But when you decode such a constructor element of the universe, you map it into the sets that's generated by this operator F families. Then there comes something which some people perceived as a shock. Erik Palmgren, he added what he considered a natural elimination rule to the Mahlo universe, and he derived an inconsistency. So personally, I was not the slightest bit shocked because I just thought it was the wrong thing to do. So this was also mentioned in Ansten's talk, Weil's notion of what was it called? Extensional determinacy, was that the term? Definiteness, extensional definiteness. Of course, we shouldn't have an elimination rule to set because we don't know all possible ways of inductively generating sets in the future. It's something that's inherently open to extension. And, also fortunately, it was not part of the theory IR. But on the other hand, we can have elimination rule for the subuniverses. That was the right place where we could have elimination rules. On the other hand, I already mentioned the internal Mahlo universe is what happens if you try to build something similar but put it inside the type of sets. Then you should really think of this as inductively generated. And the decoding function should be by kind of case analysis of this. But then it would really be natural to have an elimination rule and to get an inconsistency. So this is kind of worrying. And the way this at the time was kind of explained is the distinction between the meaning of sets and types that Per had, and you also mentioned by Ansten. That this sort of seems that this is not all right according to this conception of type theory with the distinction of sets and types as we had in the logical framework. So perhaps with IR we have reached the limit of extended predicativity. And I forgot that we wrote that in the paper, but I was a little bit surprised when I saw it because I thought from today's point of view, this is obviously not right. On the other hand, there is some kind of mystery here because the formal difference between the external and internal Mahlo universe is tiny. And the proof theoretic analysis of the two leads to, strength very similar. So why is it that one is not okay, the other is okay? So that is the mystery. And it sort of feeds into some kind of general feeling that when we have developed more general theories of inductive definitions, we all want them to follow Per Martin Löf's idea of constructivity. But actually, there is not much work on the details. Certainly, I and Anton thought about this when developing our theories, but we haven't written it out explicitly. And in some sense, this is what we do in this talk, in this paper. So let me just check what the time is. Yeah, not too bad. So the upshot of this talk is that Mahlo, both external and internal, are predicative after all. And we do this by actually first building a predicative model of the theory with Mahlo Universe in set theory, happily using non-constructive and impredicative features. Here predicative is in Anton's sense of predicative, namely inductively defined. And here we happily understand inductively defined in set theoretic sense. That's the first step. The second step will be to give meaning explanations, say that all this set theoretic machinery is in some sense inessential. But it still is very important for the understanding, I think, to do this kind of exercise in set theory. Yeah, so sorry. So the second thing we do is to sort of take out what is relevant for explaining the meaning of this theory. I'm very closely following Per Martin Löf's ideas about meaning explanations in the paper Constructive Mathematics and Computer Programming. And again, although the paper is about the external Mahlo universe, we kind of, Anton is very against publishing unproved conjectures, but here is an unproved but quite sort of likely conjecture that it's not a problem to do the same work for the internal Mahlo universe. Okay, so let's dive into set theory a little bit. So, what we need here to model things set theoretically, first we need inaccessible cardinals, in particular, if we don't assume the generalized continuum hypothesis, we have to distinguish between strongly and weakly inaccessible, and it's a strongly inaccessible ones that we need. So they are, and it's a cardinal which is transfinite, it's bigger than omega 0, it's closed under 2 to the alpha, and so this is called a strong limit, and it's regular. So it's closed under taking least upper bounds by index ordinals inside the inaccessible. So if I is strongly inaccessible, then V of I, the cumulative hierarchy, here we have V of I. So this will be, a Grothendieck universe closed under all set theoretic operations, but also closed under all basic type theoretic operations, not the universes, but all the ordinary ones like pi, sigma, natural numbers, W types, identity types. So that's inaccessible cardinal, and I will not bother about the distinction between strongly and weakly inaccessible. A cardinal is Mahlo if, in addition to, strongly Mahlo, if you start with strongly inaccessible, but let's say just Mahlo, if and only each strictly monotone and continuous function called normal function in set theory, H, which goes from M to M, has a strongly inaccessible fixed point, K kappa of H less than M. So what the picture we will draw is that we will actually need a Mahlo cardinal smaller than the inaccessible cardinal, and then we will define some function here on ordinals H, and we will find a fixed point here, kappa H. And we will need all these three levels. Up here, we will interpret the types. Here, we will interpret the sets. And here, we will interpret the subuniverses. So we can write down a set theoretic model of type theory in the way using, a little bit of category theoretic terminology, but it's not something one should worry very much. It's just a very compact way of writing down the model. What is important to know here is simply that a type, as I already said, is a member of VI, the kind of biggest Grothendieck universe. So a type depending on the context gamma is simply a function from gamma who interpret also contexts as elements of VI into VI. And terms then, closed term would just be an element of the corresponding type, which is inside VI. And then these are sort of dependent on a term with free variable is interpreted as a function from an environment into the corresponding type. Types also depend on variables, right? And then set, these are so-called context morphisms, which you can think of as sequences of assignments of terms to variables. But then we interpret the type of sets, so maybe I should write that out. Here is the set, this is type, and here we have the sub-universe. And then set is interpreted as VM. So it's a member of VI, and it's also a subset. And VI, because of the way the LF theory works, is that it has to be closed under dependent function types, but actually nothing else. But we know that this is the case because of the inaccessibility of the I. And VM is also closed under the standard set form because a Mahlo cardinal is also inaccessible. And then the structure of the subuniverse is like this. So if we take a function f, which is on families in here, it's an f, you think of this as something which takes family here into family there. And then, you can prove by the Mahlo property that it also stays inside the V kappa, and then I would call it V kappa. And now we can interpret the subuniverse as a sort of Russell-style universe, V kappa F, which is a subset of the VM. So it's more Russell style than Tarski style, although the formalism said that it was a Tarski style, but it doesn't matter because it can collapse to a Russell style in the model. And here is just a slide with a little bit what you need to do. I will not do this in detail. It's just a sort of little work that you need to do in order to start from a function on one of these Grothendieck universes, define an appropriate functions on ordinals, finding the kappa of H, and then show that because of that you stay within this smaller Grothendieck universe. Okay, so now comes a sketch of the model. So the first model, we can say, is a very coarse model. It doesn't really have much to do with constructivity. It's still very useful, I think, because it's in some sense it's very simple once you've sort of got to know the notion of inaccessible and Mahlo cardinal. But everything else is somehow straightforward. But now we're going to build a model which is useful for meaning explanations. And we will use, the idea that we should inductively generate the types. I mean, it's only some types that can be generated, some theoretic types that can be generated, only some contexts that can be inductively generated. Similarly, only some sets in the VM that can be generated. And here comes the key step, which is actually due to Ulrich Berger, a colleague of Anton Setzer in Swansea. And then you know that you define the set including set and being a subset, set being a subset of type, by the way it's inductively generated. And similarly, set has to be closed under the standard set formulas by definition. And then we inductive recursively generate the Tarski style subuniverses, which are also closed under the standard set formulas by definition. So one may ask, if we inductively generate all of this, why do we need this stuff about Mahlo and inaccessible cardinals? Well, it is because when we make an inductive definition, we have to bound it somehow. Anston talked a little bit about this in his talk, right? Talking about how set theoretically, typically you use inductive definitions on power sets of a base set. So I will use mode of presentation, which you can find in Peter Axel's article about inductive definitions. It's quite nice. It says that a rule in set theory is a pair. You start with a base set. This is what, we will use these Gothenburg universes like VM and so on too. And then a rule consists of a subset of U, the set of premises, and a conclusion, which is an element. And then you can define when a subset of U is closed under a set of such rules, saying that, if U is a subset of W and V implies that V is an element of W, then W is phi closed. And then one can prove impredicatively that there is a least phi closed set. We call that I of phi, the set inductively generated by those rules. It's only a mode of presentations because a rule set like this generates a monotone operator on power sets of the base sets. So let's just show something how, this is how you set theoretically generate the types. So you have three clauses, completely paralleling the formation rules that we have. So set is a type. It says a set belongs to type under no premises. X is a type for each side condition that X is an element of set. And it's closed under pi, and this is now the set theoretic understanding of pi types, Cartesian product of a family of sets. So if X is in a type and Y of little x is a type, then the Cartesian product is a type. But we need to bound it, so we need to say from the beginning that X must be an element of VI and Y must be a function from X into VI, because then we can prove that this is a rule set on VI. Also, the inductive definitions of the subuniverses is in some sense straightforward, but it uses an idea which I think originally is due to Stuart Allen from the New Pearl group, a type theory group in Cornell University in America. The idea there is that you get set theoretic semantics of a universe a la Tarski by focusing on the decoding function. We start with a function on families of sets, families on VM. By Mahlo property, we know that this function goes from V of kappa of F, the subuniverse, into V of kappa of F. And then we can now define a rule set for the graph of the decoding function. So the first component in the pairs is an element of the universe. You then define, after you define the graph, you define its domain. If there exists some element in the graph that is in the first component. So here we see how C naught XY is an element of U, and F naught big X big Y is its decoding. So you map C naught little x little y to F naught of big XY, provided x is mapped, little x is mapped into big X, and the function little y is, roughly speaking, mapped into big Y. And also here, we need to have some side conditions to bound the size of this rule so that you can prove that this is, we have a base set. So but you can also see that it closely parallels the definition of the equality, the computation rules for the Tarski operation. Then we come to the crucial rule here. That is, when can we say that a subuniverse is an element of the type of sets? So here is a new idea needed, because we start really with a function f on families of sets to families of sets, but we haven't yet defined sets. We can't put set in here. That would be very impredicative, right, and inconsistent actually. Well, no, it simply doesn't fit into the formalism. But the idea is now that it's problematic to assume that we start with f from families of sets to families of sets, because one of the sets will be u of f naught f1. So it's really very obviously impredicative. But the idea of Ulrich Berger was that it's enough if we require the function to map elements of u of f naught f1 to families over this subuniverse and show that they are sets. In that sense, uf naught f1 is not supposed to be in this family. So this we can actually do. And the set theoretic work is to show that this works. And this sort of complicated looking rule, it's actually just the premise that if it maps an element of the subuniverse, well, the family of such, to the family of subuniverses, then we can put uf naught f1 in it. So we get some kind of stratification of the sets because we can only put this in, after we have somehow determined this one here, but not the whole of set. But this suffices to show all the rules. One can prove, after having written this definition, that this, now we have defined the type of sets, and we can prove that every, the image of the decoding function applied to an element in the subuniverse actually returns a set, and not only something in V of M. And we can prove the formation rule. As soon as we start with any functions on families of sets, and we compose f with the Tarski decoding, then we get a function from families in the subuniverse to families of sets. And this is exactly the premise for saying that uf naught f1 is in sets. So so we can justify all the rules of the Mahlo universe. Let me see how I'm doing for time. Yeah, not too bad. Now we forget all set theory, and we only discuss the bare bones of what you need to say in the meaning explanations. First, some generality about meaning explanations. Martin-Löw's meaning explanations are expressed in terms of evaluation of expressions to lazy canonical forms. What lazy means is that it's only the outermost syntactic form that needs to be a constructor. The subterms can be arbitrary terms. So for example, 0 is canonical. Successor of A is canonical, even if A does not terminate, actually. It can be anything, or it can be 2 plus 2. Sup of A, B similarly, there is no condition on A and B, but sup is a constructor, N is a constructor, it's a set constructor, W is a constructor, and also, which is a bit new to this approach, is that set itself is an expression which is canonical. Laura, no? So that's the basis for the whole of it. So when you have a judgment, little a, big A, both can be, to start with, non-canonical. What you do is that you evaluate little a, get a canonical form, starting with a constructor little c. You evaluate also the type, big A, getting a type constructor, big C, with some arguments. And then you have some matching conditions. It should be the right element constructor to the right type constructor. So for example, 0 in N. And then you have some conditions. If it's 0 in N, there are no conditions, but in other cases they are. So let me just, so a comment here is that the matching conditions usually correspond to formation and introduction rules, usually. But today, they don't. But the W type is exactly like that. The matching condition, when we have evaluated a term and a type, we may get a canonical term here, WAB, and we may get a canonical type set. Then this is okay, provided A, which may be non-canonical, again can be analyzed to be a set, and B is a function from A to Z. And similarly, if now W appears to the right and sup is the constructor for the elements of the W types, then these are the matching conditions. So now we need to extend the usual what Per Martin Löv had in 1979 to the subuniverse. So we have new canonical forms, U, applied to this family operator, and the codes for these functions. That's all we need to add. And then we have new computation rules which exactly mirror the decoding equations that I showed earlier, so I won't go into detail of that. And let's just look at the matching condition for U F0, F1 is in set. And this is just, what we had when we took the set theoretic definition, inductive definition of the type set, which was a subset of the VM, right? The conditions were that, that if we start with a family in the subuniverse, we apply the decoding function T to it, and then we take the family operator, then we should land in sets. So this is the matching condition that you kind of check when you come to this state. I think I'll skip this rule because this is in some sense nothing new, but it's just the matching conditions corresponding to introduction rules for these subuniverses relating to the code C0 and C1. Something which is very, very important, which has maybe not been emphasized so much in the past, is that there is a tacit assumption in the meaning explanations that the process of computing lazy canonical forms and checking matching conditions must be well-founded. It's I guess because you can't really see that mentioned in Per's writing, but it's kind of clear that it's what is meant to say that a term C is considered to be an element of N if we, after this lazy evaluation and matching process, produces finitely many successors and ends with a final matching 0. And it's not intended that we should consider an infinite sequence of successors to be a good element of N. It's a sort of standard number. Maybe in Ulrich's talk it will be the case, but not in standard Martin Löv type theory. And similarly, you can hear from the very name of the W type that we should get a well-founded tree, and we don't accept non-well-founded trees as being elements of the W type. So this is maybe not a big deal, or at least we have been lulled into thinking that this is obvious for ordinary type theory. But when we come to the Mahlo universe, our willingness to bet, I think, decreases because of Palmgren's paradox and things like that. The situation is not so clear, right? So well-foundedness is a non-trivial issue for set as a Mahlo universe. And you saw that we had to go through some motions in the set theoretic model, and we had to sort of invoke the intuitions developed by set theorists in order to sort of boost our confidence in believing in the well-foundedness. And yeah, here we have, so again, I will emphasize that the matching condition for the subuniverse being in set, it deviates from U formation since we only check the elements in the subuniverse. I mean, F applied to elements in the subuniverse. If we instead tried to have this as the matching condition, then the well-foundedness condition would be broken because of Erik Palmgren's paradox in the following way. Am I running out of time? Yeah, because I think this is somehow interesting that what happens, assume that we took the formation rule as matching condition for when we try to see whether UF naught F1 is an element of set according to the meaning explanation. Then we should say that F naught big X naught X1 is in set, and similarly for the F1. For any X big X naught X1, which is a family of sets. But take now the example, so we would have to somehow check those conditions. There are, of course, infinitely many. Take the case when F is the identity operator, the somehow projection, first projection and second projection. Then the matching condition for U in this particular case would have subtrees, X naught set for any X naught and X1 T for any T in X naught, where the X1 is applied to this. And one of those is X naught equal to the subuniverse U pi naught pi 1 itself. So you see that we have run into a loop. We get a non-well-founded matching process. This is not what we want, because we want to accept this judgment. But we avoid this circularity by only matching in the image of the subuniverse. So a common misconception about meaning explanations is that people may think that we are claiming that by giving meaning explanations for type theory, we provide absolute guarantees for the correctness of type theory, the consistency of type theory, which is kind of embarrassing if there is an inconsistency discovered. But it is very important to say that meaning explanations is one thing, and justification of the rule is another. The meaning explanations are in some sense completely objective and clear, and in the vocabulary of Göran, third person, while the justification of the rules is something different. You have to somehow make it likely that the meaning explanations in the sense of this matching process is well-founded whenever you have a correct judgment. This is subjective, first person, which is in some sense how you can read this famous statement by Per Martin Löv in the constructive mathematics and computer programming paper. There are also certain limits to what verbal explanations can do when it comes to justifying axioms and rules of inference. In the end, everybody must understand for himself. This is first person. While I would claim that the meaning explanations themselves are third person. And then another thing, is that when justifying rules, we may use any means at our disposal. For example, mathematical model building in set theory. Although one may think that all of that stuff is essentially irrelevant to constructive correctness, it's such a useful exercise that aids the intuition of what's going on. And in some sense, classical set theory is so good because it's so bad. And this is because there is a big difference between the intuitions from set theory and type theory. You know, all of this kind of meta reasoning has some kind of parallel in constructive set theory, but then the notions that's used on the meta level are more similar to the notions in type theory, and maybe it helps less for the intuition. Yeah, so this slide is just to say that one can kind of, I mean, really, really important is, of course, that meaning explanation is not mathematical model building. It's not realizability model, which is a common misconception. It's sort of right, but it's not right. So the conclusion of this talk is that type theory with set as a external Mahlo universe is predicative and constructive in the sense of Martin Löw. And the way we achieve this is that meaning of judgments of the form UF0 F1 in set is not determined by U formation, unlike essentially everything else. And this is just, you know, some history of ideas, you know, started with the idea of Ulrich Berger in conversation with Anton. This idea was, there is a paper, joint paper with Anton and Reinhard Kahle, trying to develop this idea in Pfefferman's explicit mathematics. And then Anton and I wrote a paper where we took what they had in that paper and modeled it in type theory, and actually Anton implemented it in Agda. But then you get a kind of model of explicit mathematics in type theory, which is kind of quite different from what we started out with, the type theoretic Mahlo universe. And this talk is about going back to the original Mahlo universe and applying the same ideas and use the kind of classical set theoretic model building for the kind of meta-mathematical support. Thank you.